So thank you, Dr. Pim, for your wonderful presentation. Okay, so now let us welcome our next speaker, Professor Jackin Boaz Jessie, and he will present on 3D and see-through light field display using digitally printed holographic screen. So he's also one of my master's thesis advisor. And so let us know more about our speaker from Daniel.
Absolutely. So, Professor Jackin Boaz Jessie obtained his Ph.D. from the University Utsunomiya in Japan in 2013, and then continued as a postdoc researcher in the same laboratory until 2016. His research interests were diffraction theories and computer-generated holography. He then joined the National Institute of Information and Communications Technology as a researcher in 2016 to work on practical realization of 3D heads-up displays. He then moved to the Materials Innovation Laboratory of Kyoto Institute of Technology as a project associate professor since 2020. His current research interests include holographic materials, digital hologram printing, and structured light beams.
Okay, thank you very much. So now let us welcome our speaker, Professor Jackin, to present his talk.
Yeah, thank you, Professor Vijay. First of all, can you hear me and can you see my title screen?
Yes.
Okay, very well. So first of all, I would like to thank Professor Vijay for inviting me here. And since morning, we've been listening to very nice talks on imaging, especially capturing 3D information. But this one will be on 3D displays, which means not capturing 3D information, but generating 3D information. Today, I would like to show you how a digitally printed holographic screen can solve several problems in 3D display technology and can make 3D displays realize a practical reality very soon. So to get started, we human beings grow up developing certain methods and certain habits to interact with the real world around us, and such a way that they provide the most pleasing experience for us. So it will be beneficial to use the same methods to interact with the digital contents as well. But unfortunately, today we are tied down to certain preset methods to interact with the digital contents. But the time we spend with digital contents are increasing day by day. So there is a significant effort being invested in bringing together this real space and cyberspace together. And one technology that is driving this forward is AR/VR technology. And one of the important components of AR/VR technology is 3D displays. So yes, 3D displays are getting more attention, and it will be increasingly used in our lives in future. Considering technical specifications, 3D displays can be classified into two broad categories. One is a head-mount display, which has seen significant progress recently, and we already have working prototypes in our hands. But talking about head-up displays are behind head-mounted displays, and they have a lot of catch-up work to do in terms of practical realization. One of the most promising, one of the technology that has been used to implement these displays so far was stereography, but it's known that stereoscopic displays provide inconvenience when you use it for a very long time. So people are trying to move away from stereography and trying to invent new devices. The two promising solutions that exist are holographic displays and light field displays. The audience here need no introduction to holographic display. Holographic displays is where the 3D object information is recorded as a 2D interference fringes. And when the 2D interference fringes is again illuminated back, we get to see the 3D object. And light field technology or integral imaging displays is a slightly different principle. It works based on a slightly different principle, where we don't use any coherent light sources, but capture the object information through an aperture onto a 2D screen. The aperture can be anything starting from a simple pinhole array, but the most popularly used ones are lens array screens, considering light throughput advantages. Now, when the captured 2D pattern is displayed back through the same lens array, the lens array integrates the 2D pattern into a 3D image, which can be seen by the observer. So both the technologies work fine, but the major difference comes from the system specification required. So holography basically works on diffraction theory, and the grading equation immediately tells us that a very huge space bandwidth product is required in order to realize a 3D display of size, say, 20 centimeter by 20 centimeter. So existing electronic devices are not capable of satisfying these demands. So holographic still remains as a static portrait as shown in this figure here. On the other hand, considering integral imaging displays, the workload here is shared between two components, and so the demand on the display is not as severe as compared to holography. So we can safely conclude that integral imaging technology sounds more closer to practical realization compared to a holographic technology. Now, let's look more deep into an integral imaging based head-up displays. So this is a simple configuration where the lens array that is mounted on top of a 2D display converts the 2D information projected from the display, integrates them into a 3D scene, and the user can perceive the 3D image looking into the 2D display through the lens array. Now, this works well, but the issue is that the viewer has no access to the real world now, which is behind the 2D display. So in order to provide access to both the virtual content and the real world, the viewer is usually made to look through by placing a beam combiner here, which combines both the real scene with the virtual scene. But again, we can see that putting a beam combiner increases system complexity, and the system becomes significantly heavy and bulky. So one way to solve this problem is to use a 2D projector instead of a liquid screen. So this creates a separation between the display and the lens array, so that the viewer has now direct access to the real scene and the virtual content at the same time. But here again, there is an issue, because when the viewer sees through the lens array, the real world gets distorted in this figure, as you can see in the top left. But here is where the important solution provided by holography comes into picture. So when you fabricate the lens arrays as a volume reflection hologram, the wavelength selectivity and angular selectivity property of the volume reflection holograms selectively modulates only the beam that comes from the projector, but it does not affect any of the light that is coming from behind the scene. So as you can see here, whatever is behind can be clearly visible. At the same time, it modulates the light coming from the projector alone. So a 2D projector plus holographic lens array is an optimal solution to realize see-through head-up displays. And it also has several other advantages, like providing a larger viewing area, and also can be used with multiple projectors at the same time. But the advantage provided by holography does not stop there. For example, to realize such a holographic integral imaging style display, the one major problem is that the light that's reflected back from the edges of the volume reflection hologram usually end up away from the viewing zone. So what this results in is we see dark areas when viewing the display. So the conventional approach to solve this problem is to use a collimation optics. So, but this works fine, but when you try to increase the size of the holographic screen, then you also need to increase the aperture of the optics, which also consumes larger optical path length. So the system gets significantly complex. So one potential solution is to replicate the collimation optics function onto the holographic screen itself. What I mean here is that we can print a virtual curvature, means we can tilt each elemental lenses in this array virtually by a small angle. And this is not a physical tilt, but this is a virtual tilt. By doing that, we can bring the back into the view zone. The same applies in the vertical direction as well. If you introduce a tilt or curvature in the vertical direction, then we can bring all the beams back into the viewing zone. So this brings us to the key idea that instead of just using the flat lens array, we can include multiple functions into the lens array, so that we can solve several existing issues in 3D display, integral imaging display, without any compromise on system complexity. So fabricating such a holographic lens array, the simple way to do that is to use an already existing glass or plastic lens array and do a hologram recording. But this would allow us to record multiple functions. So instead we can record each lens one by one, by placing the recording medium on a XY motion stage. But again, this requires tilting the whole optics in order to record the virtual curvature and functions. So what we have done is we have used a digital technique where the light beam is modulated digitally by a spatial light modulator, which contains all the functions that is necessary to be printed on the hologram. So this allows us to print the hologram with any arbitrary function required with high precision. So before printing the hologram, the figures on the left show the display setup. We have a commercially available 2D projector and the holographic screen placed at a distance. All the display system parameters has to be preset. Based on the system parameters, we can calculate all the angles and the lens tilt as shown here. So here for a hologram of size 20 centimeter that is placed at a distance of ½ meter from the projector and 1 meter from the viewing zone, needs a lens tilt of 5 degrees in the horizontal direction, plus and minus 5 in the horizontal direction and 5 degrees in the vertical direction. So once these parameters are decided, then it is a straightforward task because all these curvature functions are well-defined mathematical functions, and these phase profiles can be easily calculated and the final hologram pattern can be calculated. So here we have calculated 200 by 200 elemental lenses, each with a focal length of 2.15 millimeter, and the size of each elemental lens after being printed onto the hologram is 1 millimeter by 0.5 millimeter. So this is a partial view of the whole holographic lens array. Now to print the hologram, this is a simplified image of the hologram. So the lens functions that are displayed on the SLM is interfered with the reference wave, and the photopolymer sheet is placed here on a XY translation stage. The recording medium is a commercially available photopolymer sheet by default, or Covestro, and the size of the recorded hologram is 20 centimeter by 10 centimeter, and it takes around 28 hours to record a hologram of size 20 centimeter by 10 centimeter. So here we can see the effect of the virtual curvature. So on the left side, without a virtual curvature, the display appears dark at the edges, but when we print the virtual curvature into the hologram, then we can see it's uniformly illuminated. Now there is one more step that needs to be done before we can show 3D object, that is to calibrate the display, because the projector is placed at a distance from the holographic optic element. So we need to align each pixels of the projector with each elemental lenses in the lens array. So we project some patterned images and we try to understand the relation between the pixel positions and the elemental lens array, and then we do a reverse mapping so that after calibration the image looks undistorted. Now here is an animated 3D scene. On the left side you can see the computer model 3D scene, and the dimensions are also shown there, and which we generate the integral images and we display it in the projector. And when you look at the 3D scene, you can see that the 3D scene is reconstructed and agrees with the computer model result. So this is a single color, but we can also do full color by using 3 laser beams and 3 spatial light modulators, 1 for each laser beam, and do the same single shot recording. And this shows the color reconstruction. So on the left you can see the computer modeled objects and their physical dimensions, and the rendered integral image. When this rendered integral image is displayed on the projector, you can see the 3D object reconstructed. So this is again an animated color reconstruction. This shows that the image in the background, the light coming from behind the hologram, is not at all affected by the hologram. It is totally passed through, while only the information that is sent by the projector is modulated and integrated into a 3D image for the viewer. So this shows that the see-through performance and color reconstruction can be achieved faithfully. Now, what we try to do is that we try to apply this as a windshield display for automobiles. So the windshield of an automobile is usually not flat, curved. So we try to see what happens if we curve the holographic lens array, because the photopolymer sheet is flexible, so it is it's possible to print it as flat and then curve it. But what happens is that here you can see the reconstruction from 2 donut patterns that are placed 3 centimeters in front and behind the lens array screen. You can see that the donut pattern in front of the screen is stretched horizontally, while the one behind is stretched vertically. This is because now the positions of the elemental lenses are not well identified by the calibration algorithm, because now they don't lie on a flat plane, but they physically lie on a curved surface. So we need to find a way to identify the lens arrays, the position of each elemental lenses accurately. So what we try to do is, we try to print small diffuse surfaces on the corners of each elemental lens array, so that they will serve as markers from which we can find the position of each lens array accurately. But then it will raise the question, will it affect the display performance? As you can see from the image that is shown in the middle, the diffusers are not at all visible under normal illumination, and the diffusers are only visible when you illuminate with in a special manner. So we use this. I will not go into the details of the calibration. So we use the diffuse markers as ground truth to detect the positions of the lens accurately on a cylindrical surface, and then we do the calibration. After using the diffusive markers, you can see that the perspective of the front and the back images are reconstructed correctly. So finally, what I would like to conclude is that we have used digitally printed hologram. By digitally printed hologram, we mean to print very large holograms of multiple functions added to it, and which helps us to realize a see-through, compact, flexible, and full-color 3D displays. So this avoids any additional optics that is otherwise necessary to realize 3D displays. And here are some of the system specifications that we have achieved so far. And one thing that we are not satisfied at the moment is because the depth of the 3D scene is only 5 meters in front or behind the scene. To provide a very good 3D perception or a very good experience, we are working on to further increase the depth to at least 10 centimeters. And before concluding, I also would like to thank all my colleagues and their affiliated institutions for their support with this work. And thank you.
Yeah, thank you, Dr. Jackin, for the wonderful presentation. So